We are continuing our discussion of big O analysis, picking up where we left last time with the official definition of big O one more time. F of n is O of g of n. Some function is in fact O of g of n if there exists positive integers c and n such that f of n is less than or equal to c times g of n for some certain range of values of n. Here it says for all n greater or equal to some given value. That was our definition. We went through that with an example. We found those values of c and n. And at the end of that example, we were able to say that that given function, I believe it was 4n squared plus 3n plus 10, we were able to say it's actually O of n squared, not because the professor said so, but because of the actual definition. And I think we understood a lot of it, but what was one of the major takeaways that we could actually leave with after that discussion? Is that c times g of n is actually an upper bound on the value of f of n. Given some function, if we say, oh, this function runs in n squared time, or O of n squared time, that n squared time, it really represents an upper bound with the knowledge that there's actually that constant c that we're putting there and that we then find. It represents a worst possible scenario of the running time. The number of operations is at worst proportional to our given g of n for large values of n. So what we want to do with that in this particular video is we want to be able to go through some examples of looking at code because we know the definition, and I say here, yeah, our lives have been enriched, and clearly sarcastic, right? So what's the benefit of this big O is we can now analyze code, and we can look at a given code fragment and say, oh, that's O of n. Look at another code fragment, oh, that code fragment is n log n, and here's why. Or another code fragment is n cubed, and yet here is the reason why. So that's what we're going to do is we're going to look at many examples of code fragments and really break down the running times of each of those code fragments using this idea of big O and worst case scenario. Very first example right off the bat, we have here two for loops. So you want to look at these two for loops, and the main thing you want to do is ask yourself, given some code, if it has some loops, are the loops nested? Are they not nested? How long is each loop running? Because we said we're going to be basing it off of some input size n. So look for n in these for loops. Here's an input size n. Here's n as well. And try to just ask yourself, before I move on in the video, how many times does that first for loop run? How many times does that second for loop run? And what's actually happening inside each one of those for loops? So what we hear about is that repetitive number of operations. What's happening over and over in this for loop for very large values of n? So in a for loop with n as part of the comparison, when we're trying to determine when to stop, such as on this particular for loop here, we're saying loop from k equals 1 to k is less than or equal to n over 2, right? In that kind of a for loop, whatever's inside that loop is going to be executed many times, right? So we care about what is inside that loop, and we care about how many times that for loop will actually execute. So let's go look at these two particular for loops here. The first loop runs n over 2 times. Each iteration of that first loop, we had one singular operation. That operation was what? It was sum equals sum plus 5. So there will be exactly n over 2 operations for this for loop. So if n was 1,000,000, there would be 500,000 summing operations in that for loop. That second for loop, it actually iterated n squared times. And in that second for loop, we had a single summing operation again. And so because of this, we can say there are actually n squared operations in that second loop. Here's that first for loop. We have that one singular sum operation, and it's going to loop n over 2 times. Let's say n was 100. This first for loop is going to run exactly 50 times. This second for loop is going to run 100 times 100 times. That's going to be 10,000 times. And each time it's going to do this singular summation operation. That first for loop, again, it has n over 2 operations. That second for loop has n squared operations. Those loops are not nested. So what do we ultimately do? We're going to add their operations. So the total number of operations is n over 2 plus n squared. And if I ask now, given n over 2 plus n squared, what is the big O of that? The answer would be O of n squared because you get rid of any of the smaller terms. So we can say the running time of this code fragment is actually O of n squared. Look at another example. Once more, we start by asking ourselves what? Are there loops? We know the input size is n. How many times are those loops running? Are those loops nested? And then try to pay close attention to what's happening inside those particular loops. So we need to actually look at what's going on inside the code. We care about those repetitive operations. So we have these two loops here. Let me actually turn on the laser pointer. We have these two loops, and we can see that they are nested. One of the loops happens inside the other. This outer loop, it loops from I equals 1 all the way to less than or equal to n and including n. And how many operations are performed at each iteration? There's some consideration, right? You have to think about that. Well, how many operations? Well, this happens inside. We have inside at each iteration another entire loop. But before moving on, we can see that this outer for loop, it's going to iterate exactly n times from I equals 1 to I equals n. Now, this inner for loop, it also iterates n times from j equals 1 to j less than or equal to n. And now we finally have an operation. We're doing x plus plus, just a single operation at every iteration of that inner for loop. So let's look at a couple of these iterations of the outer for loop. When I equals 1, what happens? What happens is this inner for loop runs n times, and each of those n times it does a single operation, right? So we have n operations of that inner for loop. Then the outer loop gets incremented, I gets incremented, I is now 2, and when I is 2, what happens again? The inner for loop again runs exactly n times, each time doing that one operation, so we have those n operations again. And so we notice that for each iteration of the outer for loop, the inner for loop runs n times, resulting in exactly n operations. And how many times does that outer for loop actually run? We already said the outer for loop runs n times. And for each of those n times, the inner for loop runs n times. What we can now do is we multiply those two values together, and we see that the overall running time is exactly O of n squared. Another example, this one's pretty straightforward, kind of really reminiscent of that first one. You have this function, and we have two for loops. They're not nested. Let's do a quick analysis of this. Look at what's going on inside the code. Again, we care about those repetitive operations. Each for loop has a single operation, x plus plus. Inside it, that's it. Each for loop goes from I equals 1 all the way up to and including n. These for loops are not nested. The first loop runs n times. The second loop runs n times. They're not nested. And each time each of those for loops runs, it's just a single operation. So what we do is we simply add together the total number of operations. Our running time will be n operations for the first for loop, n operations for the second for loop. So we get 2n, n plus n is 2n, and of course O of 2n is simply O of n because we get rid of that coefficient. Example 4, here we go. Pause the video. Ask yourself, what really is the running time on this particular method? We have a while loop. That while loop, it keeps looping as long as n is greater or equal to 0. What happens at every iteration of that loop? Pause the video and try to think about what actually is going to be the running time here. So we have this one while loop, but you can't just look at it and say, oh, it runs n times, or maybe n over 2 times, because you see what's happening here, n equals n divided by 2. Rather, this while loop, it continues to iterate as long as n is simply greater than 0. Okay? Well, how many iterations will that be? Within the while loop, that last line of code is really the kicker. It says n equals n divided by 2. At every iteration, n gets divided in half. So if n started at 100, there won't be 100 iterations because we go from 100 is the first iteration. Now we're at 50, 25, 12, I can't do division, 6, 3, 2 or 1, basically 0. So when n is 100, it only runs 7-ish times. So what can we remember from this? At every single step of the iteration, n is being divided in half, in half, in half. That should kind of clue us in, and we remember, oh, binary search, something similar. What's the running time of binary search? Log n. And any time you're dividing the input space or the search space in half at every iteration, that smells like a logarithmic solution. So how do we actually get that log? We've seen it once before. Let's actually show it again. We're going to make this new variable called original n. Original n refers to the value that was stored originally in that input, right? That input n right here. We're going to call it original n. So if n started at 100, original n, of course, will be equal to 100. The very first time through the loop, n gets set to original n over 2, right? N gets set to the original value divided by 2. If n was 100, so after one iteration, n is now 50. The second time through the loop, n, this value n right here, it gets set to original n divided by 4, right? If n was 100, then 50, then it becomes 25. Original n divided by 4. The third time through the loop, n gets set to original n divided by 8. The fourth time would be original n divided by 16. What you want to keep doing is think about, okay, what about the fifth time? Original n divided by 32. Is there a pattern? Well, there is a pattern, but you don't see it until you really look at what this 4 is and what this 8 is. And it's really, we're going to use the powers of 2. And we see after 3 iterations, which was this right here, we had original n divided by 8. But really, if we realize that 8 is 2 cubed, after 3 iterations, n gets set to original n divided by 2 to the 3. After 4 iterations, n gets set to original n divided by 2 to the 4. After 8 iterations, n gets set to original n divided by 2 to the 8. One more. How about after 17 iterations, the n gets set to the original value of n divided by 2 to the 17. So now in general, after k iterations, we can say that n gets set to original n divided by 2 to the k. And this algorithm will end once original n over 2 to the k equals 1, because at that point we will have found the value we're looking for, or we found that it does not exist. So we solve for k, because we want to find the total number of iterations. So given this equation, just solve for k. So you multiply both sides by 2 to the k, and you get original n equals 2 to the k. You have to use log to solve this. We've seen that before. And ultimately, we get k equals log base 2 of original n. So we can approximate this algorithm as O of log n. Another example. Think about this one slowly. I really encourage. Pause the video and try to really just think about what would be the running time of this algorithm. There's a lot going on here. I'll give a hint, and then I want you to pause the video again after a hint, but just pause and try to think about what might the running time of this algorithm be. Certainly we see 2 loops. That should clue you in towards something, but really study this for a few minutes and then come on back. So what's going inside the code is we, at first glance, we see those 2 nested loops, right? That would usually indicate this O of n squared algorithm. But we need to actually take a closer look at what's going on in the code and focus on what's happening with the values of I and the values of j. Well, the first thing is we see this thing right here, array of ij equal 1. That should be confusing at first. Like, what are we going to do with that? We have this outer loop while I is less than or equal to n. we have this inner while loop while j is less than or equal to n. The outer loop is going to loop n times. The inner loop is going to loop n times. Is it going to be n times n? Well, let's think about that. This inner loop, it says, and array of ij, it has to equal 1. If it does not equal 1, don't even loop. Now, we don't know what's inside this array, right? We're just told we're given a two-dimensional array of integers. We don't know what it equals. But this while loop says, keep looping as long as j is less than n, and we're going to increment j. Also keep looping only as long as array ij equal 1. What do you do with that? What should you do with that? Pause the video. Think about how you think you should approach that. And the big hint would be, this is big O. What is big O? The 3 words, worst case scenario of running time. So what we do with this right here is we can effectively ignore it, because we're going to assume, for the purposes of worst case running time, array of ij is always equal to 1. It may not be, but we're going to have to assume the worst case scenario of running time, that it's always equal to 1. So this while loop will not have a stopping condition due to this particular component of that Boolean expression. That's super important. Now, what we can also see is I and j, they both clearly increase, right? J is increasing inside this while loop. I is increasing inside the outer while loop. And neither of them ever decrease. That's important. Also very important to notice, maybe some of you picked up on this when pausing, that neither of those variables, I or j, neither of them get reset to 0. So the outer loop, that while loop for the outer loop, it ends once I becomes n. What does that really mean? The statement I++ can never run more than n times, and the statement j++ will never run itself more than n times. The most number of times these two statements will run combined is 2n, and so we approximate this as O of n. That's not enough of an explanation. As I say that, I want to look at this just very briefly a little bit more, because the next example is very much related. It's going to be super simple to understand the next example, and it might even be easier. You know what? I'm going to go on and I'm going to come back to this one to make more sense of it. Let's come to the next example and ask, what is the running time here? And I'll tell you, this is O of n squared. We have 2 loops. This code is identical to the last code with one change. That one change is this j equals 0 right here. Otherwise, the code is identical. So now we have 2 while loops. This outer while loop is looping n times, right? And it gets iterated. I increases by 1. It gets incremented at every iteration. This inner while loop, j increases at every iteration. We ignore this part. And we notice that this inner while loop, not only does j increase each time, but after this while loop finishes, and after we restart the outer while loop, now I is 1, and then I is 2, and then I is 3, at every new iteration of the outer while loop, what happens to j? J gets reset to 0. That's super important, which allows this while loop to effectively start over. These 2 while loops, they're closest to 2 for loops in meaning, right? A normal for loop would be for int I equals 0, the inner for loop for int j equals 0. So both of those variables, I and j, get reset to 0 when those for loops start. And that's what's happening here. This inner for loop, it's getting reset the j value to 0 before we start this inner while loop, which means we have 2 loops, they're nested, each one runs n times. At each iteration of the outer loop, the inner loop runs n times. This is O of n squared. But now when we come back to this example here, why is this one not O of n squared? If you don't see it yet, pause and think about it. Why is this one not O of n squared? Well, because this outer loop, it runs n times. This inner loop also runs n times. Why is it not n times n? Well, because think about when I is 0. Just literally plug in from the beginning. I is 0. Is 0 less than some value of n? Let's assume n is a positive value. Yes, it is less than 0. I is less than n. We come to this inner while loop. J starts at 0. Is j less than n? Yes. Cool. J++. Is j still less than n? Yes. Cool. J++. We iterate this inner while loop. until when we exit this while loop. What does that mean? That means we've incremented j so many times that it's no longer less than n, right? This condition is now false. J is now equal to n, and we no longer enter this inner while loop. We do I plus plus. I is now 1. It started at 0. I is now 1. We check this condition of the outer while loop is 1 less than n. Let's assume it is. But now we come to this inner while loop, and we want to ask, is j less than n? The answer is still no, because j is still that last value that j became, where we made this Boolean expression false and we exited this inner while loop because we never reset j to 0 right here. Compare this code to this code. That's the difference. So on this code, example 5, we never reset j to 0. So you have to really pay attention. This is actually just O of n. We end up executing the outer loop up to n times. We execute the inner loop up to n times, but just for a total of n plus n, which is 2n, therefore O of n. When we come to this particular code here, we now see a huge difference. J is reset every single time. That's super exciting. Let's do that a few times. J is reset every single time, which simply means what? We're going to end up with that O of n squared algorithm. Let's keep on trucking, and guess what? We have only 2 more. Let's go. Here we have example 7. Determine the big O running time of this particular code fragment. Study this in detail. We have 2 for loops. Pay attention to how many times each for loop is running. We no longer have this value in. You have to look now at the parameters. Study the parameters. Study the for loops. Check when each is exiting. How many times is each for loop going to run? Pay attention to what happens inside this inner for loop. Pause the video, spend 5 minutes, come back and see how you did here. So what we know with the parameters is we notice that we have this array of integers called a. We have an array of integers called b. And we went ahead to make this more language inclusive. We went and we sent over the size of each of those arrays. Now in Java, we don't need to send the size because we can just say a.length. Other languages, you can't do that. So we sent over the size of each array. So here's size A, here is size B. So this for loop here, this outer for loop, it's going to strictly loop how many times? It's going to loop size A times. Let me come back up here to the code. This outer for loop is going to loop exactly size A times. This inner for loop is going to loop exactly size B times. So what's happening? You might just say, oh, it's just A size A times size B, and you might be right. But let's look at what's going on inside, because here we have if A at index I, if it equals A at B at index J, stop. Immediately return 1, and this entire method finishes and returns 1. So that might end immediately, right? If A of I equal B of J, this code fragment will end immediately. So what do we do with that? What do you do with that? So the answer is we care about what? Big O, worst case scenario. We can assume A of I will never equal B of J. For the purposes of big O, we'll just assume it never happens. And therefore, we're never going to return 1. That situation will never happen, and we will execute these for loops as much as possible. So what is as much as possible? We have 2 loops. They're nested. The outer one loops size A times. The inner one will loop size B times. And we're going to end up with O of size A times size B, which is your running time. Another one. What is the running time of this code fragment? Once again, study the parameters, study the loop, pay attention to what's happening inside that loop. Pause the video, come back after 5 minutes, 2 minutes even. Really try to study this one before you listen to the answer. We have here these same parameters. We have int, an array of integers called A, an array of integers called B. We have size A, we have size B. This outer for loop is going to loop size A times. What's happening inside that for loop at each one of those iterations, right? We're going to loop size A iterations, but what's happening inside here? Do we have just one operation for each iteration of the outer for loop? Do we have two operations? How many operations is this? Well, what is going on? We're saying if bin search, what is that? You could assume binary search. If binary search, we're calling a binary search here on something, we'll analyze what that something is. If that binary search returns true, then we hit return 1, else we don't return 1, and we keep on going. So first of all, we can assume this binary search will never return true because we don't want to return 1 here for worst case scenario analysis of big O. We want to assume it's going to run as much as possible, right? But now the question is, what's happening here with binary search? Well, look at the parameters. We have B, we have size B, and we have A at some index I. Well, what is B as a parameter? That's this parameter. So B is a reference to an array on the heap. So we're sending to this binary search method, we're sending over array B. We're sending a reference to array B. We're sending over size of B, the size of that array. And we're not sending over array A, we're sending over a specific index from array A. What this really means is we're going to be looking inside array B for a value from A. Cool. So we're doing a binary search over array B, and we have the size of B. What is the running time of binary search on an array of size n? You would say log n. What's the running time of binary search on an array of size B? The answer would be log of size B. So this binary search, it runs in what speed? It runs in O of log size B. Cool. How many times are we doing that binary search? We're doing it size A times. So that's what's going on inside the code. Now we know the binary search is log n. The for loop executes exactly size A times. And for each iteration of that size 8 times, the binary search will run and it has a speed of log of size B times. So ultimately, we have what is the big O running time of that code fragment? It's size A, the number of iterations of the outer loop, times log of size B. Was that extraordinary? I don't know. Destiny, it's a horrible one. Some are destined to soar on the wings of eagles while being torn apart by beaks and talons. It's been fun. As always, if you have any questions, feel free to leave a comment, reach out. Take care, everyone.